our game. Let's make our game. This is what we got from last time. This simple game. We will delete all of this. To the right we have our speedrun timer. We'll start it. Our first goal is movable rectangle, and we will focus just on making the player. We did a game in one file, 200 lines of code. We'll be deleting most of this, not all of it, just so we have some basics. Like we can even just create a new file. So we can change this to old main, and this will be the new main CPP. And we'll see what we will use from last time. Not much. Now, the imports for sure we will need. The imports. For now, we will ignore the vector import, but this is for window, glfw for window management. This is for GLAD for OpenGL, IOStream for input and output, and these GLMs are for working with math and matrices. Next, these were only for the game. Let's see, I'm looking for the main render loop. Yeah. So we'll have void main return 0. Yeah, so it's int if it returns. Now, where is the main function? Yeah. And now if we run this, it should be nothing. Build failed. Linking main already defined. One or more. Main already defined. Oh, yeah. I think it's having a problem with this main function. Alt main. There. Okay, no errors. We're doing fine for now. Now our focus is to make a movable rectangle. Let me npm run start. I'm starting my own server for the chat, horizontal chat below. Python chat py, okay. And we have our horizontal chat. Now, we want to, we have to go through the basics, like initializing the window and the version. Yeah, creating window. If couldn't create, terminate. Use current window. Prepare. OpenGL. Set the viewport. Yeah. Let's use all of these. These are standard functions that we write every time. Nothing interesting in that. We'll change the title to Terraria player. Terraria player. Next. I'm wondering if we should directly use the vertex and fragment shader like this, or to have them in a file. Let's make it simple and have them like this. Let's have them like this. Like the other option would be like I used them before in a file here in resources, this vertex and fragment shader. Look how before they were just in files. But it's more simple to be like this. I'll leave it like this. But here, maybe I should simplify them. Yeah, maybe for now we can. Yeah, this is the vertex, this is the fragment shader. We'll see how much we will simplify them. Let's go down, and here is the initialization for the shaders. Yeah, so these ones, these values are for when if the shader doesn't compile, we store it inside these two. So here success is if it compiles the shader, and info log is just array of characters for the actual error when it doesn't compile. And here we first need to work with the vertex shader. And here the vertex shader, we first create the object, the shader object. Then we give it the source code. This right here, we give it the source code of the shader. We compile it and we check for compilation errors. This is the success variable. If it's false, then it didn't compile, and we will extract the info in our array of characters, and we will output that vertex shader didn't compile. Like, it's standard stuff that we go through every time. The reason I'm not coding it again from scratch, like not coding these lines again, is that I want us to focus on more exciting things. And we've already covered working with shaders. So this is for the fragment shader. Wondering if I should increase the font, but for now I'll leave it like that. So this is the fragment shader. We create a shader object. We give it the source code, which is our fragment shader source code. And then we compile it. We check for errors. It's the same thing as the vertex shader. It's the same thing. And now finally the shader program, because that's what it will combine all of our shaders in one single thing. So the shader program, we create a program, and look at here how it was create shader, and this is create program. It's different now. We attach the two shaders to the program, we link them, and when linking, there can also be errors. So we once again check if it was successful, and if not, we get the error message and give it to the user. And that's it. That's for the shader. And we delete the two vertex and fragment shaders that we compiled, because we already gave them to the shader program. And we do not need them twice. We already gave them to the shader program. We can just delete them. We can even experiment what will happen if we don't delete them. I don't think it will be a problem, but it's good practice, and in the tutorial that's what they showed, so that's what I'm using. So now, okay, in the render loop, we actually haven't written a render loop. Let's write one. While, yeah, I can copy this. And here we need, yeah, we want, yeah, okay, we'll leave this. We want these two lines because they're the basics. And we want the, now which lines we want? Clear color, clear, process input, swap buffers, poll events, okay. These 4 lines. We want these 4 lines because they're the absolute basics. These 2 lines clear the screen, and this line swaps the buffers. What do I mean by that? There are 2 buffers. One of them is what's currently showing, and the other is what we're drawing. So what we will show shortly. When we've reached here, we are done drawing for sure. Because here we will say draw a rectangle, clear the screen, draw a rectangle at a certain position, make it bigger, etc. So when we've reached this line for swap buffers, we are done rendering on the second buffer. Once we are done, we reach this function and we swap them. And now we are showing what we have drawn. And then poll events. I think this is just for well, I'm not actually sure for poll events, but it's not something important that we should focus on. We can try rendering. We can try running this. It should be just a simple window. Yeah, it's a black screen. What we can do is we can use colors from Terraria. I should open Krita where I have this one, and here I want to see what the color is, and we'll use this color. How can I get it? Okay, red, green, and blue. This is what we'll use. Right now we have a black screen. Here it is, and I want it to be this screen, like this color. So to achieve that, we go inside here when we clear the color, and here it's 0 for red, 0 for green, and 0 for blue. We'll change it. And this, I think, goes from 0 to 1, and it will be hard to input these numbers because they are not from 0 to 1, they're from, I think, 0 to 255. So, for example, this is red 77, and we will type here 77, but divided by 255. And the result will be a number between 0 and 1. That's how we'll get the color, 131, 131, and we delete by 255. And here the blue color is 195. 195, and we delete by 255. Now we should have this color. And here we have it. We have the sky color. We have the sky color. Now, currently, we're focusing on having a movable rectangle. Movable rectangle. So we need vertices, VBO. Let's open rectangle. I had a file source. I'm looking for from last time where we created. Oh yeah, it's directly in the here in the main class. We'll use it just for reference to draw something on the screen. I need to stand up. It's used to, but actually, we also need to set up a projection matrix. We need a projection matrix. Let me 1 second so I set up this microphone. Okay. So we need a projection matrix. So that, because why I'm saying that is because our values, or should I keep it more simpler? It's because when we draw on the screen, OpenGL expects values from -1 to 1, but it's a bit harder to render at the right spot, but okay, we can skip it. Let's start simple. It's always best to start simple. So we need our vertices. And here, yeah, we need also a VAO. We need here our VAO. It opened the wrong file. We need here our VAO and vertices. We will change these vertices. We will change most of this. Here our VAO, and let's move it to the left. So our vertices, I think we can keep it like that. Yeah, it just, the rectangle will just not be centered if we keep it like that. Yeah, it's not an issue if we keep it like that. Okay, so for quick explanation, we also need color. Okay. So we create a VBO. Actually, we can first focus on the VBO. It's easier to explain like that. We create our VBO. So first, when we create a VBO, a vertex buffer object, what OpenGL gives us to reference this vertex buffer object is just an unsigned integer. This is what we use for reference. It's just like when we have, when we, for example, here pass by reference in C++, here is the same thing. We have just the reference of the object with an unsigned integer. And here, when we generate a VBO, I think here we generate buffer object and we store the given unsigned integer for reference in the VBO variable, and then bind buffer, GL array buffer. Here I think we create the vertex buffer object, and here we give the data, which is from the vertices. And this is the main job of the vertex buffer object, is so that we can give now the data of each vertex. And what is each vertex? It's, let me show you here. And this is each vertex. This is each vertex. So to render a rectangle, we need to give it 3 vertices. And OpenGL will make the connections, will add the colors, and will render it to the screen. We just need to give it these 3 vertices. But we're rendering a rectangle, so what we're giving it is 2 triangles, so 6 vertices. We're giving it 6 vertices, which is right here. And we give it from here. We give it from this function. Then the next function, we tell it how to interpret this data. So what we're saying is in location 0, which is in the vertex shader here, location 0. Now we're directly communicating with the vertex shader. And the vertex shader is expecting a vector of size 2 that is called A position. So we have to tell OpenGL how to interpret our data so that it can give it to the vertex shader, because right now it's just an array of float values. And how will it know which values to pick for each vertex? So that's what we're telling it. For location 0 of size 2, so because in the vertex shader we are expecting a vector of size 2, that's why here we're also saying we're giving a size of 2. So it will take 2 float values each time. 2 float values for each vertex. And here we are just saying it's a float type. We're giving float numbers because we can give other types. Here this false value is not important. And here this is the stride, this size of float times 2. So we are telling it when we have read 2 numbers, to the next 2 numbers are skipping 2 float values. So here it will skip this one, and it will move here. This stride has more sense if we have other values as well in the float. So here, in addition to the position, we can store color, we can store texture coordinates. When we have more things to store here, the stride will make more sense. And here this void 0 is just from where do we start. And we've set it 0, so we start from the start of the array. These other values make more sense when we have more than just the position. But right now we've simplified it a lot. And GL enable vertex attribute array, I think just tells that we're going to use this 0 location. Finally, we bind it. Yeah, so this is the VBO and it looks fine. So why do we have, it looks like it covers everything, like we've given the data to the vertex shader. So why do we need the vertex array object? We need it because it will simplify when we have to use the data again. So right now, look at how much functions we had to call just to render a rectangle. And do we have to every time call all of these functions just for one rectangle? Well, this is where vertex array object comes into place, because it remembers once we create it from this one, generate vertex array, and we bind it. Once we bind it, then everything else that we do, it will remember it. So here we create the vertex buffer object, we filled it in with data, and all of these functions, the vertex array object remembers it, what we have done. And next time, when we want to render, we just bind the vertex array object and we draw to the screen. And that's it. The vertex array object simplifies things a lot. That's why we're using it. And I do not think you can render without a vertex array object. That's how important it is. So we have the vertex array object. We have to simplify the shaders. So for we can delete these uniforms, and for the position, we can just have it the position that we are getting. Yeah. And finally, we can set the color. We can set the color. Have to sit down. We will set the color through a uniform. We'll use a uniform to set the color. And I will explain what a uniform is for sure. But first, let's see where the code is for actually doing that. Here, we want here to set it. Also, we want to activate the shader. Where did we activate it? Shader program, yes. I want to see what was the function for activating the shader. I forgot it. Where draw shader program, yeah, GLUse program. That's it. Before we can set the uniform, we have to activate the shader, and here we're setting the color, and the color will be what will be. So we can set it as red color, or yeah, we can set it as red. And here the green color will be 0 and the blue color will be also 0. And here we have to draw. We have to draw to the screen. Draw. What was the function? Okay, here we here we bind the vertex array object, we draw to the screen, and we unbind the vertex array object. And this is what I was talking about, how, okay, let's actually run it, and then I'll say it. And here we have to the top right a red rectangle. Let's actually center it. Or we can keep it top right. We can keep it there. So here, as I said, this vertex array object, just binding it will give us, will do all of this. It remembers all of this and it does it automatically. And here we just have to bind it. And instead of VAO, we could have called it red rectangle. And every time when we bind a red rectangle and we draw to the screen, it will draw what our red rectangle is. But when we create another vertex array object and we bind that, for example, here, and here, for example, orange circle, and we draw to the screen, that's all in this. It's so simple, but it's just annoying to learn all of this. Like once you've learned it, it's simple. VO. Now we have our rectangle that is on the top right. We can now, my focus is to actually move it and to actually use the coordinates of the screen, because right now I am using coordinates from -1 to 1 on the X, and from I think up was 1 and down was -1, but it's from -1 to 1. on the X and on the Y axis. So we will change this. Instead of working from -1 to 1, we will work from 0 to I think this is 1200 pixels. And on the y-axis is from 0 to 900 pixels. That's the change we will make, which will happen through a projection matrix. Let's check if the bitrate is fine. Yeah, here it's fine. No problem. Okay. Now we want to change, instead of working with -1 to 1 coordinates, to work with the actual screen resolution coordinates. And we can achieve this in the vertex shader. We will have to use a uniform. Oh yeah, the uniforms. Here, you remember how we sent our vertex data in location 0, this thing, and we can make location 1, 2, 3, 4, etc. That's how we give data, and we can only give data to the vertex shader. And the vertex shader will give it to the fragment shader. That's how data flows. But look at how here we gave data directly to the fragment shader. This happens through uniforms. Uniforms are global. We can set them from everywhere. The problem is that each vertex will have the same uniform. So right now when we set the color red, each vertex has the color red. That's the power of the uniform. The negative side of uniforms is that each vertex will be color red. We cannot say, for example, here we want color green, here we want color blue. We can have these individual colors through locations. So here with another location, for example, location 1, to set it as color. Here, for example, color, we could have done it like that, and each vertex could have its own color. This way, but in our use case, each vertex has the same color, and it's easier to use uniforms. That's why we used uniforms. Okay, that was a quick intro on uniforms. Let's create our, here it should be matrix 4, I think. And here projection. We will create a projection matrix. In order to change the coordinates, we need an, I think, orthographic projection matrix is what it's called. Like, I don't know the details, I've just remembered it. I just remember it. And here we will multiply by the projection. Here we multiply by the projection matrix, and now we have to give this matrix. We'll give it inside where we use the shader. Where? Here. We use the shader, and here where we set uniforms, we'll use the same projection matrix as last time. It's a standard thing that we do all the time. Here we create the matrix, and this is just the identity matrix, and we always start with the identity matrix. Always start with it. It's just simpler that way. And then we actually, no, this is for the transformations. Yeah, with the transformations we start with the identity matrix, but it's still early for that. We have a few minutes until that. Now for the projection matrix. GLM, the library we imported here, which is just math functions. It has a function to use, which is orthographic. It just creates a matrix that converts numbers we give from 0 to 1200 and from 0 to 900. It converts them from 0 to -1. It converts them from -1 to 1. So here, these values now will not be top right. They will be top left, and they will be quite small. They will be quite small. We need to actually set the uniform with this. And here is also like this function where we set the color, GL uniform. Here is once again GL uniform. You just have to set the type of the input we're giving, because OpenGL functions don't have, I think it was called, what was it called? Oversizing. I'm not sure what it was called, because you know how in programming languages you can set a function and you can declare a function and give it arguments, and then you can declare another function with the same name, but the arguments are different types. And but here there isn't something like that. And for each different type you give us argument, there's a different name for it, but it's always the same functionality, GL uniform, where we set the uniform for the shaders. Here we have to get the location of the uniform. So here we're searching for the color uniform. And here we're searching for the projection uniform. That's this function. And it outputs, I think, an ID, and we're giving it as an argument to the first function we called. It's maybe a bit complicated to understand when seeing it for the first time, but it's I've written it like that, so it's just on one line. I could have easily removed this and set it in a different variable, so it's easier to read, but I've picked it to just look better. And here we give the projection matrix we created, and this value pointer is just so OpenGL understands the matrix, because I don't think we can directly give it. It's something like that. Like all of these things are not what's important. Like it's important just to understand what's happening. All the details are not needed until they're actually needed in some kind of an issue. But we haven't reached an issue, so we continue on with the basics that we know. That's how I've learned the fastest OpenGL. And now when we start, the rectangle should be top left and it should be really small. And do we see it? Maybe I should scale it. Let's also add transform, because right now the rectangle is 1 pixel, a size of 1 pixel. So let's actually make it bigger. Let's make it bigger by creating a transformation matrix and by setting the transformation uniform with the transformation matrix. And we have to create it, that uniform, inside here. Here, transformation, and here we once again multiply it. And the ordering is really important with matrices, because they are not, I think it's called associative. When we change this order of multiplication of matrices, the result will be different. So transformation matrix is just so we can move around, rotate, and scale our objects. because when we want to make changes, for example, our current goal is to make a movable rectangle. When we want to move a rectangle, we will not every time change these vertices. We've set them once, they will stay like this forever. What we will do is create a separate matrix, and we will multiply the matrix by the vertices values in the vertex shader here. This is the power of vertex shaders. You can do a lot inside each vertex shader. There are other vertex shaders. There's a geometry vertex shader that I think can create new vertices just within the shader. But I haven't used one, so we will stick with just vertex and fragment shader. They're really powerful. And here is the actual vertex position. It's a vector of size 4, where we just focus on the first two values, x and y. And to move it and scale it, we multiply it by a matrix, the transformation matrix. Doing it this way, we don't have to change these values. And the matrices are not something complicated. You will see me copy and paste reference values. I just have to find them. Like, I you can see me from the start. I haven't remembered any syntax. All I'm doing is copying and pasting previous syntax, and I just know how to use it. That's what I focused on. I haven't focused on actually remembering the syntax. And here we will float size. We will scale it. We scale it. Okay, so first we start. For transformations, we always start with identity matrix. We start with identity matrix, which does nothing. We can actually use it. We can actually use it. We use a transformation matrix. That is just the identity matrix. And I'll show you what it does. All it does is nothing. Here, we still cannot see the rectangle because it's too small. Because our identity matrix, when we multiply it by any vector, the vector stays the same. We do this way because we will use other matrices that we multiply with the identity matrix. If we started, you know what? We'll do an experiment. We'll leave it like this, where we use an identity matrix and we multiply by matrix for scaling the values. And we scale by size of 100. So now the rectangle should be of size 100 instead of 1. And here it is. It's size of 100. And the width is 1200. So we should be able to put here 12 squares like this. Now, let's do an experiment to see the power of matrices, the identity matrix. But I think we cannot even do the experiment because, yeah, let's see, can we remove the identity matrix? What will happen if we don't use an identity matrix? It doesn't work. Like, we need the identity matrix as a base because this scaling matrix, we expect to have another matrix, a starting matrix. And why? Why do we need a starting matrix? It's so that we have other matrices that we will use. Like, to scale it, to scale the vertices, we multiply by this matrix for scaling. And how do we rotate? There's another matrix for rotating. How do we move around? There's another matrix just for moving around. And here it is, transformation matrix. So the matrices for moving, scaling, and rotating expect a previous matrix. I have to stand up. They expect a previous matrix, and because they always expect a previous matrix, we have to start with some matrix. And what's the best matrix to start is the identity matrix that does nothing. It's just our starting point. Enough about matrices. Here, let's move it. We can move it. Let's see here. Where can we move it? Center of the screen. So this is 1200. So divided by 2, it's 600. But our origin is top left. So to center it, we need to subtract half of the width and height of the square. And here it's 900 height. It's 900 height. Divided by 2 is 450. And minus half of the width of the rectangle, it's 400. And the order of multiplying matrices matters. First, I think it's scaling, then rotating, then translating. And that's what we're doing here. We're first scaling and then translating. Translating is always the last step. I'm not sure if rotating or scaling is which one of them is the first one, but translating is for sure the last step. And here the square should be in the center. Now we are using a square, but we will create the player. We'll create the Terraria player, which is more of a rectangle instead of a square. So what we can do is we can change the vertices so that the initial vertices, instead of a square, it to be a rectangle. How we will do this? Well, so right now we can open a whiteboard. We can open a whiteboard here. So now, currently we have a square. We have a square, and these are the values. So the first vertex is 0 on the x and 1 on the y, and it's actually two triangles. So it's like this. It's two triangles. I just want to see which are the actual values, which vertex it is. So on the x, so before it was like this, where the origin is here, and plus is like this to the right, and I think to the up. But here the origin is here. The origin is here, and plus is here, and plus is here. This is the standard for OpenGL. This is the standard for actual game engines. This is just because of our multiplication by the projection matrix. Like it's standard for the origin to change like that. And so right now, 0 on the x and 1 on the y should be here. 0, 1. I think. We'll see if we are correct. 1 should be here. 1 on the X and 0 on the Y should be here. 0 on the X, 1 on X, and 0 and 0 0. Here it's 0 0. Okay, and we need a rectangle. Do you notice how here there are 4 vertices, but we gave OpenGL 1 2 3 4 5 6. We gave it 6 values, but we're actually working with 4 vertices. We're repeating some of them. Why? Well, we're actually first defining each triangle. So that's why we have to give 6 vertices. We're saying this one, this one, this one, and creates one triangle. And then we repeat this one, this one, this one, another triangle. That's where the repeating comes from. If you don't want repetition, you can use EBO, which uses indices. So with EBOs, you can just write the vertices once, so 4 vertices here, and you can say use this vertex, this, and this. Then use this vertex, this, and this, without having to write them again and again. It's like having a reference to them. But in a simple project like our one, we will not use one because we don't want to overcomplicate things. Now we want a rectangle that looks like the player. So what we will need is here another square. Another square. And actually, what we will do is it will be like this. It will be rectangles, but they will be like this. They will be like that. And here is 0 0. And here it will be on the X 1, Y 0. And here its size what should be the size? Should this be 1 and this 0.5? Because when we scale it up by 100, if this is a 2, it will be 2 times what we have scaled it. It will be easier if it's without multiplying by 2. So it will be better if this is 1 and here 0.5. So we can have this to be 0.5. And here it can be 0, 1. And here here on the X is 0.5 and 1. That's it. Okay. And so so this is 0, 1, 1, 1. So this should be 0.5. This should be 0.5. So every time before we had a 1 for X, it will be 0.5. So we have to change only that. Every time we have here 1, it should be 0.5. It should be, oh, I'm 0.5. Now let's see if we have a rectangle. And here we have a rectangle. Yo! Yes! We have a rectangle. And this will be our player. We'll add textures and animations later on. Have to sit down. First, we have to make it movable. And for now, I just wanted us to be able to move it left and right. That's what I want. I want us to be able to move it left and right. And we can abstract it away in a class. But I was thinking how exactly it would be. Why do we need the abstraction? It's so that we can keep track of values. So for this rectangle, we can keep track of its x and y. So when we press to the right and when we want to move it 10 pixels to the right from its previous position, we need that previous position. And with classes, if we have a player class, it will be easy to just say, give me the x-axis of the player. So that's why we need to abstract it. We need... Yeah, let's now abstract it in its own class and let's render it in the same way. And then we will add movement. Let's hide this one. We don't need it. And let's increase font size. We'll increase the font size because now we're working with just one file. Now, let's create a class player. This is placer. Player public. And let's see what Visual Studio wants us to use. So yeah, it's taking it from my other file. So player has size X and Y, has a color, and in the constructor we set the X and Y, and we set the size and the color, and we initialize it. Here we have its video. Here it should be 0.5 on the x-axis because we want a rectangle, not a square, for the player. And here we do the same thing as before, where we bind the video, generate it, create the video. Yeah. And for drawing, it's also the same thing. We bind and draw. Here for the drawing. And we haven't even used the shader program. We need the shader program for setting the color. Yeah. And for transformation matrix. We don't need this. We we don't need, we don't need this because we will use our player object here. We'll define player, and here X and Y will have the same ones as before. Size 100 and color 1 for red color, 0 for green, and 0 for blue. And these transformation matrices, we will copy them because we will use them here when we draw. Here when we draw, we need GL use program, shader program. Now, we need to use the shader program when we want to change the uniforms. We will change the color. We will not set the projection matrix. And here GLM, I think matrix 4 transformation equals GLM. What was it? I can't remember. I don't know the syntax. Like, I do not know the syntax. Thanks for following. Oh, come on. What's with that name, man? That name's not cool. Sorry, but I'm banning you. Your band, man, you cannot go on with that name. Actually, because of that, I'm also going to hide this chat window below because I don't have control over things like these. Display capture, like I don't have control over you guys, so I have to hide this. And I've banned that person. It's most likely a bot. It's most likely a bot. Okay. So we will not be able to look at the chat, sadly. Next. Now I've forgotten. Where were we? Yeah, in the player. In the player. Where were we? Yeah, in the drawing. Yeah, creating the transformation matrix. Like GLM transformation. Yeah. For translating, we will here just use the X and Y, and here the size. And we don't need this projection matrix. We set the color and transformation matrix, and that's it. And that's it. And now we've created the player. Here we don't need this. We don't need to set the color. We will leave the setting of the transformation matrix as just the identity. This will be just initializing it with something, because it will initialize it, I think, with zeros, and it will remove everything. We can even experiment to see what happens, but let's first see our player draw. And let's see, we should get the same thing as before. We have the same thing. Look at what happens if we don't initialize the transformation matrix with something. I think it will handle it, but after the first frame. Yeah, okay, it handled it. Then it's fine. Okay. That's what's cool about these experiments, is that you can learn new things just by experimenting. Now we want to move it, to move the player. We want to move the player. We can create, for example, another function, void move, which gets float x delta and float y delta, and that's how much the x and y will change. And that's it, I think. We should multiply by delta time, because right now it's dependent on how fast, like for my machine, frames go really fast, and so the movement will be really fast. This will be called a lot of times. But if we multiply by delta time, the movement will not be dependent upon the how fast frames render. But we can leave it like this without delta time. Or okay, let's let's add it, delta time, and let's multiply by delta time. Yeah, I'm just not sure. Okay. Next, we want to process input. So here, let's process input. We'll create a function that takes a window and gets a player and a delta time. And delta time is just here, float delta time, float current time, and float previous time. And so delta is just current minus previous, and when we've rendered everything, we update the previous time. And here we give the delta time to process input, which is a function that we have to create. And let's make it. We'll VS Code. No. We have to make it ourselves. Let's create it where? Here. It should be void process input, and it takes a window. Okay, this code has a suggestion. Let's see it. So it uses W, A, S, and D. I'm using the home row keys. So for me, W will be K, S will be J, A is to the left. So for me, it should be H, and D for me should be L. Because I have learned Vim motions, and now it's easier for me to use them for movement. So we move the player. This will be quite slow of a movement, and we also don't want to move it up and down because it will be like a platformer. For up and down we just have gravity and space for jumping. So we remove J and K, which is for up and down. And here we will move, we can have float speed, and here just have, so to the left, yeah, we have to subtract, and to the right we have to add. So here speed, and here speed. And I think that's it. We can start it. I'm pressing, nothing happens. Why? Nothing happens. Why is it not happening? We're calling the move function of a player. Sure. And here we're, do we have to call it in different? No. Window. You know what? Is it just the speed that is slow? Let's increase the speed a lot. It's the same thing. Okay. Let's see what the issue is. Let's see the issue. Here we are calling the here process input, we're giving it the player, and here inside the player we have X and Y, and here when we move we change X and Y. We can try changing it to having this. Let's see if adding this will change it. But the size worked, so I don't think this would be an issue. The size worked. I don't think this is what the issue is. But let's see. It still doesn't work. Where was pros input? Press. Get key, player move, delta time. Okay. Movement. Translation. Okay, every time we draw, we change the transformation matrix with the new X and Y value, and the Z value is always 0. We scale it, fine. We set the color uniform and the transformation uniform. Yes. We bind the VO and we draw to the screen. Are we missing something? Let's see our past player. In the past, what did we do? we did the similar thing. Have to stand up. This is really confusing. I think we can try a few things. We can remove the delta time as an experiment. Because if delta time is 0 because of my wrong calculations, the x and y should be 0 as well, so it's not it. Yeah, let's look at process input. Yeah, if git key window here window. Okay, we can go to the move, and here we can remove delta time for simplicity. Okay, it's delta time the issue. Delta time is the issue. Delta time. Okay, current time is 0. Oh, we are not updating current time. Here, we need to update current time. We need to get glf get time, which gives seconds. And now it's quite fast. We need to make it slower. So in our speed, let's remove 1 0. And here we have a movable rectangle. This is it. We have a movable rectangle. Oh man, this 1 hour just for one movable rectangle. Yo. We can go into a quick break. Yeah, we can go into a quick break. Now, yeah, we can go into a quick break. Okay, I'm back. Uh, I'm back, but trying to set this up. Stand up. And here we have a movable rectangle. We have a movable rectangle and we are still far off our goal. We're still quite far off. Yeah. Open widget. Yeah. I'm just looking at the stream. If it's all right. Should be all right. Okay. Excellent connection. And this looks fine. Let's continue on. Now, the next step is gravity. The next step is gravity. It would be better if the next step was platform, so that something can stop our descent, but okay. We can work with this as well. So for gravity, we... how will we implement gravity? We can, every frame times delta time, just move our object downwards. So we can do here, we can have float gravity, and let's set it to, okay, let's set it to that. And we can just have it unconditionally. Unconditionally change the y axis to gravity with delta time. And yeah, we run this. Look at how slowly it falls. Oh man. Why is it so slow? Like 9.8. Oh, it's because it's seconds. Yeah. It's because it's delta time is in seconds. And I think we have to change it to some other thing. Okay, let me sit down and we will see what speed will fit best here. What speed will fit best for the gravity? For gravity, we can... let's multiply by 100. So, like this. By 100. You know what? Let's have it like this, by 100. This changes, instead of delta time being in seconds, it will change delta time to being whatever is smaller than seconds. Microseconds. Oh, now this is a lot faster. Okay, now we have gravity and it's really fast. Let's just check it and let's add a platform. Let's add a platform and then jumping. Now, we can actually commit gravity and push. Okay, let's add platforms. Let's add platforms. I had to turn off my heater. Now, let's add platforms. For platforms, we need to create another abstraction, another object. Here, instead of player, we'll have another class that we will call block, a single block. And it will have public values. It will have what happened? It will have float x, y, and size. A size will be 16. Or a bit higher than that. Color, yeah, it can have color. Constructor, view, init is the same things as before. We could have abstracted this away, but it's just two classes. We will repeat it. It's not that big of an issue. And we can set my battery is turning low. Just 1 second. I have to charge it. It's the battery on my phone that I use to just monitor if the stream is alright for you guys. Because when there's only when there's 0 viewers, if there's a problem with the stream, it's on me. But if there are other viewers, it's easier to spot if something's wrong. Now for drawing, we have draw. Here we use the program. Let's use from our player yank and see now. Okay, we need transformation for moving the object, for scaling it. We set the color, set the transformation, we bind the VO, we draw it. And that's it. Yeah, very simple. Very simple. And what else? We need to create now. We need to create how many blocks? We want 3 blocks under the player. So block 1. And here it set it sets it to the green color, but we can use color black. And here it moves it. The size it sets to 100. Let's leave it at 100. On the y-axis, we want it to be 350, let's say. And here, let's set it as the same y, as the same x. Oh, we need to draw it. We need to draw it. Block 1, draw. We need to draw it. And why is it colored? It shouldn't be the color red. It shouldn't be. Let me turn on the heater because it's still too cold. Why is the color red? We set the uniform to... Oh my... We've hard-coded it. We're ignoring the color. Oh my god, we're doing it for the player as well, I think. We've hard-coded it. Here it should be color red, color green, color blue. And in our block, it should be the same. If we had abstracted this away, this drawing that repeats and this initialization that repeats, if we had abstracted it away, we could change it in one place and we don't have to copy and paste everywhere, but not that big of an issue. Also, let's make the block smaller. Now it's 100. Let's make it 50 size, and let's move it more downwards. Oh no, to move it downwards, we need to increase the size. So 750, let's say. And here we have it. For it to be in center, here it should be 600 minus 25. It's half the width. So it's minus 25. Here should be 5. And here should be 7, I think. Just so it's centered on the X. It's not that centered, but okay. Now we need to have collision, which is the hard part of platforms. We need to add, let's add 2 more blocks. Let's add 2 more blocks. Let's have them, this to be at, how can we move them so they are right next to each other? So we can have this block as 500. Let's have this as 550. And let's have this as 600. Let's leave it as that. Oh, we have to change the name as well. Block 2, block 3. And here, you know what, we can, okay, let's, I was thinking of having them in an array, but let's leave it as that. Now we should have one long platform. Here it is. We have one long platform. We can make it even longer later. Let's right now, or yeah, let's increase it now. So let's create, we need vector, include vector. And here we will need to also initialize them. Because when we create a vector of blocks, it will use the default constructor, and we don't have a default constructor. And yeah, we will need to have a set position, and yeah, okay. So let's add a default constructor inside for our block. And here we just say like this. And here we call block 0, 0, 0. That's it. And we need to have a set position. Set position like this. And now we can create a vector of blocks. It's just so we don't have to, like, I want to create a few more blocks. I don't want to have them like this manually. I want it to be a bit more automated. So a vector of blocks of size 10. And I think we have to use std vector. And in here for like this. Yeah, we can do it like this, where we yeah, we can do it like this. So we don't need even a set position. Yeah, we can just ignore the default constructor and just have a new one. I was thinking of calling each object that's already created into set position, but we can try it like that. And here for each block, we draw it. Now we should have 10 blocks. But this this messed up. Here it should be times the size. So here 50. Okay, and now we can add 10 more blocks. Here let's int blocks count. Here blocks count. And here blocks count. And here let's change it to 25. Let's change to 20. Perfect. Now we have a platform, a simple platform, and let's have collision. I want us to have collision. How will we add collision? We can add it in our movement. We'll set a new function that we call check collision. No, this is for outside bond. Or what? How can we can use this guide here, collision detection. Why wasn't there any network? There should be network. Yeah, this is what we will be using. This collision. This is between rectangles. This is between rectangles because there is a different one between circle and rectangle. There's another one, bit more complicated, that is between circle and rectangle. We don't have circles, so we will use this one. This one is between two objects. Now, here we have an issue. Because we didn't abstract away drawing, and when we check collisions, oh, and this function I think should be outside. This function should be outside of our player because it checks collision between two objects. How can we do this? You know what? We can, instead of it can be here player, and here can be platform. It will be function specifically for them. Yeah. Let's copy it and let's have it inside our game. Where exactly? Here? I think here. And here it will be between layer and what did we call this? Block. And here we rename this to player and this to block. And here for the size we could have used just a square, and when we increase the size, instead of scaling it with the same value, to have different values. We could have simplified it to have one game object. Yeah, we can do it for the next stream. Here is just size. And here it's X, and here X. I just have to change these to match my own. And this is also the X. And here is the Y. Here the Y. Have to stand up. Okay. Now we check for collisions. Let's check for collisions. So that when we fall on the platform, we don't move past it. But this just checks for a collision. The problem is that this just checks for collisions. And nothing happens after we check for a collision. We have to decide what to do when the player has collided. Yeah, we have to figure it out. So where should we put it? It's here actually. Yeah, here. When we, yeah, but we can collide to the right and left. We can collide to the right and left, which is an issue. And we can collide upwards as well. So it's just after every movement. So every time we move, yeah, it's every time we move. Oh, come on, this is so complicated. And we move. Yeah, okay. We can do it. Yeah, we can. Every time when we draw each block, we can check collision, player and block. Now, if there's a collision, no, we don't change the player color. What do we do when there's a collision between a block and a player? We can set it to stop moving, but it will get stuck like that. If we can, how do we handle collisions? I'm not sure. Or we can say if there's collision downwards, or we can, yeah, let's draw on this. Let's draw on the screen. So here we have the platform and we have the player. We have the player. And the player will move downwards. Like player. So the player moves downwards each frame. And here it has moved downwards and we see there's a collision. So, and it can happen. Look, it can happen like this and like this. Now, it can happen here. There's a collision with one of the blocks. And it can happen here. There's a collision. Like here gravity is constantly moving us downwards, and you are pressing to the right. Is it possible to have collision with both? Okay, let's say it's only with one of the blocks. We can... So what has to happen is when we press here, right, it moves to the right. It checks that there's a collision and it moves you back. So it undoes the previous movement. But the issue with this way of doing it is that if we just undo the previous movement, for example, here, gravity, from here, it moves directly here. And if we undo the gravity, we move back here. So we will be floating. And here, if we move to the right, it will undo us here and we'll never touch this wall. I think this is called pixel perfect collision, where we are able to move perfectly. We can do it like this, where we undo the movement. Yeah, we can store in the player the last movement. And if there's a collision, yeah, but no, we'll do it differently. This is the wrong way to do it, undoing the movement. Because if there has been gravity and we move to the right, like we will lose one of the movements and it's not all right. What else we can do is when we collide, to move it just enough. Right now we are just checking that we are collided. Since we are collided, let's match. Yeah, but we have to know if the collision is coming from down or up, because here, when we have jumping, here the player jumps, we have to move the player down. It complicates things. How can we do this? How can we do it? And that's why in the guide they have collision detection and collision resolution. And here for the breakout game, the resolution is simple. You're just destroying blocks. You're just not rendering them. But for our case, we have to move our object. Okay, there's a collision. I need to move downwards. There is a collision. We can try to figure out if it's coming from below or upwards. Yeah, we can just check. If it's from below, right now we're just checking for a collision. If it's coming from below, we match them. We try to match them. So our y value plus our height should be equal to the y value of what we're colliding with. If it's to the right, we're matching our x plus width to match the x of what we're colliding with. The problem is if we're colliding to the left, then it should be... Yeah. Okay. Let's go here. And we can have another function that's that we can call we can have another function. We don't need this. We can have another function here, check collision. We can have void resolve collision between player and block. What? It auto-completed. X overlap, Y overlap. It auto-completed. Resolve collision. Let's see if it's right. So if the player X value, so let's open our whiteboard. So if the player X value is, let's have as well X, Y starts from 0, 0, increases like this, increases like this. It starts from here. And here is the origin for the player. And here is a block. Here it's origin. So what it's saying here, player X is less than player block. And we are setting the overlap to be player X plus player size minus block X. Else, so we are checking if this dot is, so less negative is to the left. So we are checking if this dot is to the left of this dot. And there, the issue is that I don't think this is correct. Here we are just checking if there's a collision on the x-axis. And here if it's on the y-axis. And the issue with that is that, okay, it only checks if there's a collision on the x-axis, but we don't know if we came through here or came through here. So we don't know if we should move it. So we can check the overlap, how much it is. But you know what? Look at it. Yeah, we can differentiate. Let's once again do the check. Here, let's delete all of this. Like this. And if the collision is on the X, yeah, but can it be on both, actually? Can it be on both? You know what? What do we call this one? like this. It's a collision both on X and both on Y. So like we don't know, this is all we see. We get just a snapshot of the current situation and we don't know, did we, like here, once we see it, we know that we possibly should move like this, but it can move like this as well if we're like here. Like we know if it's through gravity, by playing the game, we know we're falling like this and we should be moved upwards. But the game only knows this, it doesn't have the previous context. Man, collisions are hard. Collisions are hard, man. How can we... How can we do this? How can we do it? It just has this screenshot. We can... You know what? We can check which one is smaller, because most likely if it's through gravity, you'll be here. And it's like... Look at how here for this block, let's say this is its... We can calculate the block's center. And we can check, look at this right now. This, we're above the center, so we will move it upwards. Because if it's through gravity, most likely it will not catch it this much. Like this. It will probably like be a little bit. And this gives us a hint that it should be moved upwards. But yeah, and if it's like this, it's a little bit here. If it's like this, yeah. So we can calculate the difference, each difference. And we're looking for small positive difference like this one. So here we can subtract our current X and the block X. So this is if we are coming from the right. Let's see. Let's delete this. If coming from right, left, up, and down. Now, if we are coming from the right, and we want to set here float player right, and it should be, so the player X value, and this X value is smaller than this one. Now it should be block X plus width minus that. So block X plus block size minus player X. Yeah. And this should be left. If we're coming from the left, it should be player X plus player size player minus block. And here should be player up. We can call it just right, from right, from left, from up. And here it will be similar. So if it's coming from up, it should be player Y plus player size minus block Y. And here it will be block. And here minus player. Now, we go through each one of them. And we look at which one of them are positive. And we will pick the smallest one. But can it be both? So if it's both, like this, and it will move it like this. No, we will. Okay, so let's have float x difference equals it should be if any of these is positive and the smallest one. So, but if it's like this, yeah, but if it's like this, yeah, like this, where can man, this is hard. What? So like this, there's no collision, but one of them will be positive and one of them will be smaller. For sure. For sure, one of them will be positive and one of them will be smaller. I'm wondering how we will calculate the difference. We can, because if it's like this, like there should be a collision for sure. So let's say it's let's move them. And So if it's like this, from up will be positive. Oh, we need to change it here from down. Here. If it's coming from up direction, from up will be positive, from down will be negative because it's subtracting this big num. It's subtracting this point on the y-axis minus this point right here, which is smaller. I think it should be the opposite. Here it's if it's like this, from up will be this point minus this point. But the other will be positive as well, I think. Like if it's like this, yeah. Only if it's like this is negative. Man, there are all kinds of weird cases. I should have read something on this. I cannot wing it. Yeah, when I made English as a programming language, this is what people meant. Like, programmers are not struggling with the syntax. We can figure out the syntax. What we're struggling is with solving problems, like solving this problem. That's what we're struggling with. Yeah. I want us to try a naive approach, even if it's the wrong one. Like, what can we do? That's the right approach to this. So we have this thing, this, and this, each one of them. If they're... Oh, you know what? We can say... let's say that the difference is from right. But it should be... do we have C++ min max? I have to stand up. Stand up. Now we can... Let me set up the mic. Now we can... Because here we're trying to resolve the collisions. Here I'm taking the difference from the right, if I'm coming from the right, and I want to have like minimum, the maximum between 0 and from right. But is there a STD? STD? What? STD max. I think we have to import. What do we have to import? Include algorithm. include algorithm. Okay, and now what's the issue? Probably it doesn't accept floats in float. F. Okay, and now if you know what we can say, from right, we can do it right here. It's we can clamp it from left, and now we can say by default to be from right, from right, and then x difference to be the smallest one. Yeah, and we do the same for the other ones from up, but here, yeah, it's the same. From down, and then float y difference, and y difference is the smallest of the two. And what do we do from here? If x difference is smaller than y, we change the player x to that. If it's the y, if y is the smallest, we change the y. Okay. This should... oh my god, this was so much code. Now, when we see there's a collision, we try to resolve it. Now, hopefully this works. Hopefully this works. What? What happened? It moves it here to the right. It moves it here to right. There's a mistake somewhere, but it happens so fast. Oh, I saw it. It fell here and it moved here to the right. It moved here to the right and it continued falling off. So it's moving to the right. It's moving on the x-axis. It's resolving it, but not in the right way. You know what? Let's keep only the y difference. Let's keep only the y difference. It doesn't work. Yeah, let's focus on the y difference only. Let's focus on the y difference. How do we do it? We are 2 hours in and maybe we're close. Maybe we're close. From up. So let's focus just when we're coming from up. So we are checking. There is a collision. We have checked that there's a collision, and we're seeing that player y plus its size. So here, this point, and we subtract this point here, and we get a small value, positive value. And here we get, oh, okay. And here I think the problem is that we clamp it to 0 and the smallest is the 0 one. Yeah, I think that's the issue. Yeah, that's an issue. Both 0. And the other is this point minus this point. So here it's the other value is block y plus its height minus player y. So all of this minus player y should give a bigger number. And we are saying you know what? Let's actually simplify it even more. Let's comment this out. Let's comment this out and let's try it like this. Oh, the gravity moves it too much. That's the issue. The gravity is moving it too much, I think. Let's change the speed of the gravity. Oh, no, let's change here. Let's make the gravity slower. Now what happens? What? What? What was that? It... What? Here it... What? Oh... I have no idea what's going on. So we are calculating player y because we are adding it. We have to subtract it. We have to subtract it. Oh, that's an issue. Because if it's from up... Oh, you know what? If it's from up, we subtract it. Yeah, okay. Let's... I have to switch to downwards. I have to move down. Yeah, I can... we have to subtract it. Yo! 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 Yo, we have collision! What? What? We have collision. We have collision. Yo. I didn't expect to reach it this far. I didn't expect to reach it. Oh. Yo, look at... currently we're always checking just on the y-axis. That's why when we collide, it teleports us up. But we will fix that. We'll add collisions to the right and to the left and to the up. I believe we can do this. Oh my god, man. Oh. Okay. Let's move on to jumping and have a quick break. Let's have a quick break. I'm back. We're back. Yeah, everything looks fine. Yeah. We have collision, man. We have collision. Working. Now, we need to focus on jumping. Let's see how we can handle jumping. Let's see how to handle jumping. We have to first check if the space has been pressed. And if the space has been pressed, to move upwards and the gravity will bring us down. I was just checking if the streams are working correctly. Twitch follower, another follower that we have to block. Okay. So now we have to check for if we have pressed the space bar. Process input and how to do just pressing. Process input. Let's see in our past version. I managed to because here in GLFW I do not know how to make it only when it's pressed once, because here if I add the space bar we will just continue lifting upwards. I want it to be on release, but I don't know how to do it. There is here to check if it's GLFW release, but for me it doesn't actually work. So I've made my own naive solution. Here it should be space. And here if lock movement return, and here lock movement true. And here we move it upwards with speed. Now this should probably work. No. Where is the issue? Already defined in there's an issue with our boolean because of old main. We can delete our build and we can start again. What's the issue? Hopefully I didn't break it. Target missing executable. Okay, we will okay, let's here change it to let's change it here something else. Here we will leave it as lock movement lock movement like this. What? Oh. Here it's not Python. Here it's not Python. We need the curly braces. Now it falls here. What was that jump, man? I think we don't need delta time here, right? Like, why do we need delta time for jumping? Oh. Let's have this as 100F. Oh. What? Because of the gravity? Is it the gravity the issue? Oh, I think we have to the way we're doing it now is not okay because we're just teleporting upwards and it should be gradual like the gravity. So when we press space, we should change the gravity to be negative some number, and it gradually goes back to how it was. as regular gravity. We can... So kind of like velocity. Man, this is really hard. Isn't there jumping velocity 2D? How do people handle velocity? Apply small upward while jump. Yeah, we have to apply small upwards acceleration. Set vertical velocity to 10. On jump release, climb vertical velocity to 6. Friction. What? Oh, yeah. Yeah. Friction is what will... yeah. We have... Yeah, this makes sense. Let's have float friction, and it will be like, I don't know, 0.5. Let's have here, instead of speed, velocity. No, it's float velocity y equals 0. No, let's... how do we do it? We have a velocity and it's the gravity. Like it's always the gravity. Yeah. Let's here gravity, and when we jump, and here we always apply this velocity y, and when we jump, we subtract from the velocity a value. So oh, yeah. We don't need to lock. Yeah. We can go without it. So velocity, while we're holding space, we're removing from velocity speed times friction. Let's try it like that. I think this is not enough. Yo! Okay, let's wait it until it falls down. But right now, we can go upwards however we want, which is an issue. I want it to be limited. I want it to be limited. Half. When we press it once, else we apply friction. Okay. Let's have it as if lock movement, no if return, else lock. True. No, it should be. And we have to, I think, reset it. Yeah, else. It can be without an else. Lock movement equals false. And here the difference is, like here we remove friction. No, you know what? It will be float jump velocity. Yeah, and here velocity minus jump velocity. Here we are setting jump velocity to speed. And thank you for the follow. And we, every time we set jump velocity to be, we multiply it by friction. Yeah. What? Oh. It should be else, for sure. Else. Yeah. I need to stand up. Let me set up the mic. Okay. Now, let's try this. Oh my god. Why? Jump velocity. Let's set it to 1, 2, 3, and one more 0. I think the friction is what's the issue. Let's try it like this. It's once again just teleports. It once again just teleports. And if I hold space, it stays like that. Oh my. I think this is out of my league for sure. And it's something... it's something that... I should read up on. It's something that I should read up on. No. Velocity times time plus acceleration by time. What? Let's use some naive approach. Like let's... yeah, but we need to also check if we are stepping on the ground. To only jump if we are on the ground. So we should have a player check if below him there's a object. If if we can... yeah, let's focus on jumping for now. Let's focus on jumping. Jump velocity. Of... it's hard to solve this issue. Let me increase the gravity. Let's add it here 50. The issue is if we keep pressing space, we keep moving upwards. That's the issue. We can... and the upwards velocity gradually decreases. Man, why is this so hard? Upwards velocity jump 2D. How to jump? Upwards jump force. He's using a rigid body that automates a lot of calculations. I want more directly. Square root jump height times gravity scale times -2 mass. Oh, there's a mass as well. No way I'll be able to code this. Okay, what's the best thing we can do? What's the best thing we can do? We have some jumping. We can leave it like that. It's not the best. We can leave it like that. We have some jumping. We can try adding player texture. We can try adding player texture, or we can leave it as this, and next time, like, maybe leave it as this, and for me to check online resources on jumping, moving. For texture and animation, add remove blocks. We can leave it like this. Like, we're 3 hours in. I don't think we can finish on time. But you know what? We can try. We can try a bit more. We can try a bit more. Let's add player texture. Player texture. Let's add player texture. And resources. Let me one second. Yeah. Am I here? Yeah. And now we go to downloads. This thing. This is the player. Okay, let's open Aspirate and let's open this. And let's, we'll start with this default one. That's what we'll use, the idle one. And what will be the size? Let's see, can we check what's the size through this? And we can see this size is 21 by 30, I think. This is 16. How much is this? Is it correctly done? I'm wondering what the size should be. If it's like this, this is 15 by 24. It should be 16 by 32. Yeah, like this. For our square. It will be like that if we're going to use it. If we're going to apply the texture. But I'm not sure. Or because what I'm wondering right now is that our mesh is like this. This is our mesh. And if we put the texture, it will put it like this. Whereas I want it to be like this. More to it. Which has to be done by manually getting the values. You know what? I can directly save it like that. 15 by 24. But the issue is that this one, like this is 15 by 24, but this one is this one is I think this one is 16 by 20. Oh no, it's also 15. No, it's 16 by 24. Yeah. So I'm not sure. So this is on the X, it's 16. I'm not sure what should be the width and height. This one is 15 by 24. This one is 15 by 25. I'm trying to, because we will map the texture to the rectangle. Yeah, let's actually move this one like this. we leave jumping like that. Like what we got. We leave jumping like this. This is the jumping we're working with. Like if I continue to press space, we lift up and we can jump in the air, but that's all we know right now. That's all we know right now. Here for this one, for the player texture, let's just do what we can. Let's cut out this one. Let's create a new sprite. Create a new sprite, and we will export it as player PNG export. Where does it export it? I think here. Let's have it player export PNG. And now if we go here in resources, we should have player PNG. Yeah, player PNG. So now let's add a texture. Let's add a texture. And how will we work with textures? So inside our player, we can... Where's our player? This. And here for our vertices, we want texture coordinates. Now, texture coordinates are a bit different. We have to go where? I want to see how the texture coordinates mapped, because the origin is a bit different. Yeah, I think here the origin is bottom left. That's what I was talking about. So we can check here, and here for the player. No, where did we do it? Here. Here, this is for creating the mesh. Now we want to map to the texture. And the texture is this one. No, let's delete this one. Let's just picture. Let's just print. We will print the screen. Okay. And now we have to look at the coordinates. 0, 0, 1, 1. 0, 0, 1, 1. This is 0, 1. This is 1, 0. Yeah. And this is the triangle. Should be like that. So let's... so here, instead of 0, 0, we have 0, 1. And... yeah, so look at how we will do it. Here we copy these values, we paste them, we copy these values, and we paste them. We copy these, paste them. Paste them. Paste. And here we paste as well. And what I noticed is that the y coordinate is inverted. Wherever here we have 0, here we have 1 for the y. So that's what we'll do here. Here we just inverted. We inverted the y. And here every time we have 0.5, it's a 1 on the x-axis. So here it's a 1, 1, 1. We have the texture coordinates. The issue is that our other coordinates for the ball, we don't have a texture for the block. You know what? Let's add a texture for the block. Here we paste this one and we have to make it like the block one. We have to make it a square. Here, and to make it a square, we just have to change 0.5 to 1. Now, we need to set a texture. How will we achieve this? Player and block texture. We have a player texture. I want a block texture. Home. Tiles. I had prepared some tiles. And here, this dirt texture, that's what we'll use. Let's just copy it. We copy. Let's create new one. Okay, paste. We save it as dirt, as block pin, block, and we export it as block PNG. The platform will have a texture as well. And here, for the texture, we need, I think, unsigned int for the texture now. Texture. And let's look at, I need to open the chat, and we need to check, just looking if there are comments. No. Okay. We need to check Visual Studio, open recent, OpenGL, and here is where I've stored some, here is all the syntax for OpenGL that I've stored, just so I don't have to figure it out again. I know what these functions do, I just don't know the syntax. And that's why I've labeled it like that. So we need a texture. For that, we need an image loader, which is another library. Will this cause issues? I think not. We can even delete the old CPP file. The old main. we can delete it. Uh, it's happening like this because we changed the vertices, but we didn't change OpenGL what to do with them. It's just, it thinks this is one vertex, this is another one, this is another one, this is another one. We have to tell it that now we have texture coordinates. But before that, here we we want to create the texture. So here we load the image, set a variable, activate texture, bind loud image data, free image, and if it didn't work, yeah. Now we will set up the texture. We will set up the texture. Here width and height. Yeah, okay. Now here we need to, this will extract, we need here resource path. Here this will take the width and height of the texture and the number of channels. And this one is to flip the y-axis because there is a difference between this library and OpenGL, how they interpret the y-axis. But I think we can do it in the main function. Now we can do it in the main function. Let's say here. Now yeah, data, this is the data. I need to stand up. Stand up. Now, we load image file name. Here it should be resource path player png. And here the texture variable, it's texture. Here we I think this should be geo texture 0. Here we bind the texture. Here we bind the texture. And then we load, we need to load PNG, RGBA, width and height. Yes, generate map. We'll go over what these things mean. We need to free the data, and if it couldn't load, we need to console out. And now we have the texture, and we need to set it in the when we draw, we need to set the uniform. We need to set the uniform. Flip. Predefined set texture color. How do we... What was the uniform? Yeah, we can activate the texture and we can bind the texture, and we need to geo uniform, shader program, texture. It's just texture. Yeah, but here it should be texture, I think. Oh no, I think we don't need to set a uniform. Yeah, I think we don't need to set a uniform. Like, I need to see my past fragment shader, but here we should have the texture. But how exactly did we have it? Resource, our past fragment shader. Here, texture. Texture, we have our texture, or just one texture, and we need this. Like, this is the color. If it's the alpha equals 0, if the alpha equals 0, we discard that. This is how we have transparency. But I'll have to add these squiggly lines here as well, here as well, here, here, and I need this one here, 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 like that. And in the fragment color, we will multiply by the text color. And what will happen if we run now? Oh, we are not giving the texture coordinates. But I'll be right back. I'll be right back. I'm back. Should be... Yeah. I'm back. There's audio. Okay. Now we should tell OpenGL how to interpret the values. Here we... where is it? Here. Now we have to set location 1. Here size 2 floats. Stride is 4. And here it's size of float times 2. This should be it. And what else? Oh, we need to pass along through the shaders. Now in the fragment shader we want here layout, which is texture coordinates, and we want here out text coordinates vector 2, and here we set texture coordinates to be a texture, and here we want in vector 2 text coordinates. Once we make it work, I'll explain, but let's see. We need to change the blocks as well. I should have made... I had to make a game object and not have it like this, but we're working with what we have. If I abstracted away game objects, it would have been a lot better. Because now the changes we made, we have to do them once more. The same changes. And having repeating code like this, having code being repeated like this, easy to make unnecessary mistakes. But we're still learning, so we'll continue with naive approach. Here we copy all of this and we go to the block. Here we have to make texture. In our draw we have to activate and bind the texture, I think. In our draw, and we also need to tell OpenGL how to interpret the data. Where is it? We have to tell it here, and we delete this, and here it should be in block PNG. That's it. Let's try it again. Undefined variable texture 1 fragment shader linking field. undefined variable texture 1 in our fragment shader. Fragment. Oh yeah. Oh yeah. Here and here should be text coordinate. And here, yeah, it should be like that. Is there an issue? Fragment shader. Cannot call a non-function. A non-function. Cannot call. What line it is? 8, I think. Texture. Oh, yeah. We have to change it to texture 1. We have to change it to texture 1. And here when we don't set it, what? Yeah, it's multiplying by the red color. We'll change it. Here. We'll, for the color, we'll have it just white color. Because multiplying with the white color will leave out the, yeah. It's blurry. We need to set the filter for the texture here. We bind the texture. We need to set it so that it's not so blurry. Where did we do it? Where did we do it? Set texture. Yeah, we need these things. I'll explain what we did. Bind texture. And here for the filter, we want nearest. Nearest. And here, nearest. This should... Okay. Nice. Yo! I think it's a bit squished. And it's constantly moving, I think, because of the collision. Let's see why the blocks are black. Why are the blocks? Yeah, we have the coordinates. We have the coordinates. What's the issue? We have set it to block PNG, and we should have a block PNG. Block PNG. Yeah, we have a block PNG. Oh, because of the color. Because of the color. Because it's black. We need to... Where's... Here. We need, once again, a white color. And now once we run it, we should have... yeah, but it's pixelated. We want to make it... once again to be the filter to be nearest when it's stretched. Where's the block? Bind texture here. And now this is what we have. Kind of works. Player texture. Okay. Oh! I moved the window and the player fell down. Look, collision stops working if we move the window. Look. Look, now when I release, it disappeared. Oh, if I move it really shortly, oh. If I move it really shortly, nothing happens, but for longer movements, like collision is over. I lost my life, my speed running. Okay, now I would like to have animation. Oh, let's go over explaining quickly what happened. So for textures, we added these coordinates for the texture because for each vertex, here for each vertex, we had to say where to map it to the texture. Because here it's obvious that it should be this one to this one, this one to this one. But in some cases it's not obvious, like when we have texture atlas. Like if we have this thing. When we have multiple blocks, we could set the coordinates for this one. Or this one. That's why we need texture coordinates. And the issue is that they start origin bottom left, here. And our origin is top left. Like this common issue. So for each vertex, we had to give texture coordinates. And that's what we did. Next, we added here a connection with another location on the one. And here we changed the stride from 2 to 4 because here we check for the x and y of each vertex. It's of size 2 from the 0th position here. So we get 2 floats. And then we skip 4 values. That's the stride. We skip 4 values. 1, 2, 3, 4. And we start here. And this is the second position. And this is what we're doing. This is for the positions. And for the other location, on location 1, we are taking once again 2 float values, but we are starting from here, from position 2. We're starting from here. So 2 float values, and then a stride of 4, we skip 1, 2, 3, 4, and start from here. So this is texture coordinates. This is what we did here. And this goes inside our vertex shader here in location 1 as a texture. The issue is that textures are for the color, and vertex shader doesn't deal with the color. We need the fragment shader. But the values need to pass through the vertex shader, so we have to pass them to the fragment shader. So in order to pass them, we need a variable with this out, because it's an output. It's our output. And we need here the same variable with the same name and same type, but with in for input. And we need to match this output with what we're getting from location 1 in here. This automatically sets it in our fragment shader here, texture coordinate. And so once we have the texture coordinate, we use this uniform. This is the actual texture that we are currently binding to the texture that we're currently binding. We get its color by using the coordinate that we got and the texture, using this function texture. And if the color, the alpha of the color is 0, we discard it. This is for PNGs. If we didn't have this, it would show a black color. And then the final color we will show is multiplying a color with the actual texture. We could delete this if we want. We can just leave the texture color, but this is helpful if, for example, we have a grayscale texture, and by just changing the color, we have lots of different textures. This technique was used in the breakout game here. Breakout. It was used for here. For each of these things, each block is just one texture and just the color has changed. For generating the texture object, here we used this function of a library we loaded here, stdb image h. This is just one header file with lots of functions, and we use it to load the texture data, and here we get the path of the player PNG, and this gives us the width and height and channels of the actual texture. We generate texture object and store its ID in our unsigned int texture variable here, like the VAO. And where is it? Here. Then we activate the this geotexture 0. There are a couple of ones like this, like geotexture 1, 2, I think up to 30. I think up to 30, 31. But we use 0. And we bind the texture. So I will not go into this one. There's no need to explain this one. We bind the texture. We set the filters to geo nearest instead of linear. This is for pixel art. If we made other games, we would use linear and it will make it. And there's even an explanation here. Textures. Here. Look at how nearest is blocky and linear is blurry. And we need the blocky one for pixel art. And we set the filter here. Then we actually load the data into the texture. And we generate a MIP map, which is not needed for 2D. Let's delete it and see if it works. Yeah, it's not needed for 2D. It's for 3D when you are far off or close to the texture. It will generate higher resolution texture and lower resolution texture. So when you're far away, it will use lower resolution texture. It generates it automatically, but we don't need it for 2D game. And then we free the data that we have stored in this. And if there is an error, fail to load texture, actually this error we can move it before deleting, like we can move it here. And we did the same thing for the block here we can delete this and we can move this here, and that's it. Now I want our we need to have it here. And here we need to have it after we load the data. Now our goal is to have animations. Oh, come on. Our goal is to have animations working. But before animations, we could make it to flip the image. We could try to flip the image when we press to the right and to the left. But how can we achieve this? Like when we press to the left, we could leave it as is, and to the right to multiply it by -1. Can we... is there OpenGL flip texture? Flipping a texture. Is there something to flip the texture? Is there a function? We could... Oh, the texture coordinates, we can just multiply them by... We can invert them. So... yeah, but inverting doesn't work because there are no negative values. I'm not sure how can we flip. Like one idea is to only invert the x, the horizontal coordinates. So here we target from 0 to 1, and we can flip them where this one is here. So this is this one. I need to stand up. Not sure how we can... I'm not sure how we can invert. Not sure how we can invert. Because here these coordinates should become from 0s to 1s. No, only the x. Only the x coordinate should become from 0 to 1. This should become from 1 to 0. Yeah. But I'm not sure how to do it, and I think we'll leave it at that. Yeah. We'll leave it at here. So let's go into showcase. This is what we have. This is what we have. We have jump, we have collision, we have moving left and right, we have textures. The only thing we didn't manage to do is animations, and we couldn't flip the texture to the right and left, and we cannot remove and add blocks. But this was where we left off. And also when we hold space, we continue to fly. We can jump, continue to jump even in the air. And when and there's only collision downwards. And also if we hold the window, a collision stops working and the player falls down. This is where we managed to end at after almost 4 hours. Okay, thank you for watching. See you next time. And let's end stream.